In Chapter 16, Section 4, we'll look at Green's theorem, which is going to take a line integral and transform it into a double integral, which we have some experience in. So if we look at problem 1, it's going to be one of these where it's going to step us through it, and it says our vector field f is minus y in the I direction plus x in the j direction over x squared plus y squared. And it's going to say, show that the dot product, the integral of the dot product between the vector field f and a differential vector r is equal to 2 pi for every positively oriented simple closed path that encloses the origin. Okay, so first off, let's write what Green's theorem is generally. So basically it says, if we have a curve, I'm going to draw it a little differently than what they have shown there. So let's say we have this closed curve, and we call that C, and we're going to consider counterclockwise to be positive and clockwise to be negative. Well, we can transform this curve C into the region D, which would be everything enclosed by this closed curve C. Use a different color there, otherwise it's going to be confusing. Okay, so region D. So what Green's theorem states is this. We can take, well, first off, if P and Q have continuous partial derivatives then we can rewrite the integral, the line integral about C of P dx plus Q dy as the double integral across the region D of the partial derivative of Q with respect to x minus the partial derivative of P with respect to y. dA being the area. And we're going to notice, just like we did in the last section, that we take the j component and take its partial with respect to x, and we take the I component and we do the partial with respect to y. So it's kind of swapping what we might normally think as far as the partial derivative goes. So if we have this vector function, so it breaks this down, it says, okay, but in this one we have two curves. We have curve C, which is this counterclockwise curve that goes on the outside. So here's C, it's oriented this way. And then C prime, it's kind of hard to see that. There's a little apostrophe on this little c. It has a counterclockwise inner circle also. So we've got this little circle here, this hole. Okay, so we're going to add those two curves together, noting that C prime is going to be negative. Okay, so we're going to get, okay, so we're going to have, because it's a hole, so we're going to take the partial q partial x minus partial p partial y, just like Green's theorem states. And so we have to perform these partial derivatives. So if we take, and they did partial p partial y for us, that's right here. So we just have to find partial q partial x, which would be the partial derivative of the q component is the j term, so it would be x over x squared plus y squared. So again, let me point that out. We're taking dq dx. dq is the term in front of the j term, and in this one it's going to be this x and this entire denominator. So if we take the partial of this formula with respect to x, we have to do this as a quotient rule So we're going to have f prime g minus g prime f all over g squared. And f prime would be the derivative of x, which is 1, times g left alone, which would be x squared plus y squared, minus g prime, which would be 2x, times f left alone, which is x, all over x squared plus y squared squared. Okay, so we're going to get, this is going to be 1x squared plus y squared minus 2x squared on top, all over x squared plus y squared squared on the bottom. And this numerator, we can subtract 2x squared from 1x squared, and we'll get y squared minus 1x squared all over x squared plus y squared squared. And I believe, yes, we just have to type in this into the box. So they just want the numerator of that partial derivative, and we've got it there. Okay, then, so that's a quarter of the work. We just had to find, well, half of the work, I guess. They did partial p, partial y for us. We did partial q, partial x. And what we're going to notice is that these two terms are exactly the same, but they're opposite sign. So we have y squared minus x squared over x squared plus y squared squared. And we have y squared minus x squared over x squared plus y squared squared. With a minus sign, it's kind of hard to see in between them. They're exactly the same, they're opposite, so this gives us 0. So because this is 0, we can equate these two line integrals from up here and say that, okay, these must be the same result. So I can either go around this outer curve or around this inner hole, and those two line integrals should be the same. Okay, so then that's what we're going to do next, is we're going to actually calculate. They're going to say, okay, assume r of t is n cosine t I plus n sine t j for t between 0 and 2 pi. And so we're going to actually calculate, like we did in the last section, the function evaluated at this vector dotted with its derivative. So if r of t is n cosine ti, the derivative of that would be minus n sine of ti plus n cosine tj. And let's see what they want us to do. So they want us to dot this with the function evaluated at r of t, and the function at r of t, so we have to replace x with n cosine t and y with n sine t into this function. So we're going to get minus y, which would be minus n sine t in the I direction, plus x, but x is n cosine t, and that's in the j direction, divided by x squared, which would be n squared times cosine squared t. So I'm just squaring this x term. So this is like x, this is like y, replacing that into here. Then we're going to have plus y squared, which would be n squared sine squared of t, and that would be the denominator. And so we're going to have, let's see here. Okay, so we are going to, I got to use color on this one. We are going to dot, so we're going to multiply this term into, try to follow me here, this term. So imagine if we multiplied those, you would get minus n times minus n, which should be, I actually wrote it here, minus n sine t minus n sine t. So that's those two terms there. Now, we're going to have this denominator show up right here. This is one of them. And then we have plus, color here, we're going to take this term dotted with this term. So notice how the denominator is used twice here. So we're going to get n cos t times n cos t. So we just have to type n cos t in there. And then this n cos t is right here. And then this is the denominator again. And what we're going to notice is that if you expand out this numerator, let me see if I can write that down here. If we were to expand this out, we're going to get n squared times sine squared plus another n squared times cosine squared. But we can factor out an n squared, and that would leave sine squared t plus cosine squared t, which is just 1, so this is n squared. So this whole term, we've seen this many times in this course. Sine squared of anything plus cosine squared of the same argument, same variable, is 1. Okay, so that the numerator is n squared. And then similarly, the denominator, we can also factor out an n squared, and we have the exact same thing, cosine squared t plus sine squared t, which is n squared times 1, which is n squared. So the numerator is n squared, the denominator is n squared, those will cancel to just be 1. So this entire integral collapses into simply from 0 to 2 pi, which are the bounds on t, I kind of covered it up, it's hidden right there, of 1 dt. So this would just be antiderivative of 1 dt is t from 0 to 2 pi, which would equal 2 pi minus 0, which is 2 pi. And so we prove that. Okay, so the first one is kind of got a lot going on because you've got this trig stuff going on. But hopefully if we do our accounting correctly and keep track of everything, we'll see that it works out perfectly. Okay, that's problem 1. Okay, in problem 2 we're going to do Green's theorem. So we have the line integral of x y squared dx plus 5x squared y dy. And so we are going to transform that. So we have line integral x y squared dx plus 5x squared y dy. We are going to change that to the double integral across region D of the partial derivative with respect to x of the j term. So it's going to be 5x squared y. Then it's going to be minus the partial derivative with respect to y of the x term, which would be xy squared. And then we say dA. Well, this is going to give us the double integral over region D of partial 5x squared y with respect to x would be 10xy minus partial xy squared with respect to y would be 2xy across region A. Okay, but we need to get a sense of what this region A is. And they tell us that C is the curve that is a triangle with vertices 0, 0, 3, 3, and 3, 6. So let's draw that. Everything's in the first quadrant. So we have 3 points, 0, 0, Then it goes to, let me put some hash marks in here, 1, 2, 3, 6. So it's going to go to 3, 0, 2, 3, and then 3, 6. So 1, 2, 3, 4, 5, 6. Oh, a little bit in the way here. So 3, 6. So the triangle, I've got an error here. I see the error. This is not 3, 0, it's 3, 3. So let's fix that. 3, 1, 2, 3, about there. 3, 3. Okay, so the triangle goes from 0, 0 to 3, 3. So the curve goes along this way, then it goes straight up, and then it goes back to the origin. And that does matter, how the arrows go. So this order of these vertices is important. Starts at 0, 0, goes to 3, 3, up to 3, 6, and back to the origin. Okay, so this is region A. Actually, it's region D according to this letter right here. Okay, and so we're going to try to figure out how do my x and y vary. So it turns out that if you do slope formula, and I'm not going to go through this, the line segment, so calculate the slope between 0, 0, and 3, 3, turns out that that's the equation y equal x. Okay, then we do slope formula and point slope form, so you can do both formulas to find the slope of this top line between 0, 0, and 3, 6, and you should get y is equal to 2x. Okay, so what we're going to have is, this is going to become the double integral from x to 2x, so that's how y varies. The bottom y curve is y equal x, the upper y curve is y equal 2x, and then our x just varies from 0 to 3. And we always want the numbers last so that we actually get a number at the very end. So we're doing y first, so we have to integrate 10xy minus 2xy with respect to y, then with respect to x. And now this is a double integral that we could have done a week or so ago, or however long ago we first looked at this. So we would have 0 to 3. Antiderivative of 10xy would be 10xy squared over 2 minus, this is a 2, now the z, minus 2xy squared over 2. Oh, I'm making my life harder. I could have combined this and called it 8xy. I'll get the same answer though. Dx, limits of integration 0, x to 2x. So I am going to actually do this now. Let's do that so my life isn't as challenged. We're going to get 8, which I'm going to pull out. X, it's actually 8 over 2 I'm going to pull out, because there's a divide by 2 in both those terms. And it's going to be xy squared from x to 2x dx. This will equal 4, 0 to 3, x times 2x squared, which would be 4x squared, minus x times x squared. And so we're going to get 4, 0 to 3, 4x3 minus x3 would be 3x3 dx. This is going to be 12. Antiderivative of x3 is x4 over 4 from 0 to 3. 12 divided by 4 is 3 times 3 to the 4th minus 0 to the 4th, upper limit minus lower limit. And so we get 3 to the 5th basically, which is 243. So we have the line integral for that particular set of curves would be the same as the double integral of those set of curves, and its value would be 243. Without units, we can't really interpret that, but it's some kind of area over whatever the region is formed by those curves. Okay, and that's problem 2. That is going to be how we do most of these problems, so we'll just kind of practice this over and over now. Okay, problem 3 is pretty much the same approach. We're going to start by graphing the function. So we have C is the region bounded by parabolas y equal x squared and x equal y squared. Y equal to x squared is a parabola pointing up like this, and x equal to y squared is a parabola pointing to the right like this. This would be x equal y squared. And so the region we want, and I wish I would have blown this up a little more, is this region here. So we're going to notice that it touches, they both touch at 0, 0. And if you put those equal to each other, they will also touch at 1, 1. So that is the region we're going to solve using Green's theorem instead of the line integral. So we're going to have a double integral over this region D, right here, of, we need the partial with respect to x of the y component. So the y component is all of this. So it's going to be 10x plus 7 cosine y squared minus partial with respect to y of the x component, which is 3y plus 7e to the square root of x, and then we have dA. And lucky for us, like cosine y squared would be messy, e to the radical x would be messy, but all those messy terms are going to go away because the derivative with respect to x of this first term is just 10. So we're going to get double integral 10 minus the derivative of the second term with respect to y is just 3. So it's super easy integral. This is going to be 7 antiderivative, or double integral of dA, which we're going to write as dx dy, but we've got to decide which one we should have first. So it turns out, I mean, you can go either way here, but I think the way I did it was I solved for x. So I said x equals y squared is on top, and x equals square root of y is on the bottom. And so what we would have is, we would integrate this from, okay, let's first write this one as x would be the square root of y. And we're going to do the antiderivative of, now when we do x, we have to think left and right, and it's right minus left. So the rightmost curve is the blue curve, which is root y, so that's on top. And the leftmost curve is the green curve, which is x equal y squared, so that goes on the bottom. Normally we do top minus bottom, but when we're doing this in terms of x, so our equations are in terms of y, we look at right minus left, or right on top and leftmost curve on the bottom. Okay, then our x is very simple, it just goes from 0 to 1. Or our y term, excuse me. So this would just be dx dy. And so we're going to get that as 7, 0 to 1 of x from y squared to square root of y dy, which is 7, 0 to 1 of root y. So we're replacing x with these upper limit and lower limit. So it's square root of y minus y squared. And that's going to be 7. That's really y to the 1/2. So if you take the antiderivative of y to the 1/2, it's y to the 3/2 over 3/2. Minus y squared would be y cubed over 3. But we're going from 0 to 1. So we would get 7 this would really be 2/3 times 1 to the 3/2. So dividing by 3/2 is the same as multiplying by 2/3, minus 1/3 times 1 to the 3rd. So that's all the upper limit. Then it's just going to be minus 0 minus 0. So 0 is going to kill both terms off. And so that's what we have. So this is going to be 7. 1 to the 3/2 is 1, times 2/3 is 2/3. 1 to the 3rd is 1, times 1/3 is 1/3. So we get 7 times 2/3 minus 1/3, which is 1/3, which is 7/3. And that would be the answer for that one. Okay, so looked ugly, but the kind of messy terms, the nonlinear terms all went away in the partial derivatives, so it really isn't too bad. Problem 3. Okay, problem 4 says use Green's theorem to evaluate the line integral of f dot dr. Check the orientation of the curve before applying the theorem. It says f of xy equals y minus cosine y, x sine y. C is the circle x minus 9 squared plus y plus 2 squared equal 9, oriented clockwise. So recall what I said at the beginning. Clockwise orientation means we're going to pick up a minus sign in front of our double integral. Let's draw this picture. So let's find out what this thing looks like. So we have a circle 9 units to the right, and 2 units down. So the center of this circle, so if I have a circle like this, its center would be 9 comma negative 2. And if it's equal to 9, then the radius equals 3, which is the square root of 9. So this circle over here at 9 comma negative 2, and its radius is 3, so it's going to go 1, 2, 3. There's a dot there. 1, 2, 3 dot here. 1, let's see. 1, 2, 3 dot down here. 1, 2, 3 dot over here. So this circle looks like this, and it is clockwise, so it is going this way. And so this is region D, and so clockwise means we're going to pick up a minus sign. Okay, so with that picture, that should help us later on. Let's run this through Green's theorem. So we're going to have the double integral of the partial derivative with respect to x of the y component, which is x sine y, minus the partial with respect to y of the x component, which is y minus cosine y, dA. So we're going to get double integral. Partial here would just be sine y. The x would go away. The partial derivative of this one would be 1, partial derivative of y, minus the partial, so this might, let me put parentheses here, this minus is going to distribute a couple times here. So this is 1. The integral, the partial derivative of cosine is minus sine, but it's minus minus sine. And so what we get is sine y minus 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 triple minus y, which would still be minus y. So we're going to get, let me kind of cut to the chase here, this is going to be minus 1. Now where did I pick up the minus sign? Where did I put that in? Yeah, I should have, because this clockwise, I should have carried a minus sign the whole time. Okay, now, boy, let's make sure I don't lose you here. This is negative double integral of sine y minus 1 minus sine y dA. So this triple negative sign will leave 1 minus sign in front of the sign. We have sine minus sine, those two cancel, and we're just left with minus 1. Okay, and then we have dA. Okay, but what we want to do is we want to change this. Actually, we don't want to change this. So this is equal to, the two minuses cancel, and 1 times dA is just dA. This is just the area of region D. So there's nothing magical about this. This is the area of a circle of radius 3. Doesn't matter that's been shifted away from the origin. What is the area of that orange circle? It is just equal to pi radius squared. But we know the radius is 3. So this is just pi times 9, or 9 pi. And because there was a negative inside the integral that canceled with the outside, we get a positive area here. This is it's kind of interesting in this section. Because line integrals consider direction, you can have things like double integrals, which we think of as areas. You can have the answer come out as negative. In fact, we'll see that in one of the problems later on. Okay, so that's problem 4. Okay, problem 5 is going to have us calculate work. So work is going to be the line integral of f dot dr, but we are going to transform that through Green's theorem into the double integral of those partials with respect to that area. So what do we got here? We've got some vector field, and we're moving a particle from the origin along the x-axis to 3, 0, then along line segment 0, 3, and then back to the origin along the y-axis. So once again, we want to draw what's going on here. And this is pretty similar to one we saw earlier. So it's going from 0, 0 to 3, 0, 1, 2, 3. Then it's going 0, 3, and then back to, okay, so back to the origin. So this thing is going to start at the origin, 0, 0. It's going to move to 3, 0, this dot right here. Then it's going to go up to 0, 3, this dot up here. Then it's going to come back to the origin. So the order goes from here to here, along that line, from here to here along this line. Oops, should draw it like that. Then from that dot back to the origin, so it looks like this. This is region D. And we can see that this is counterclockwise, so that's a positive orientation. Okay, so we need to just set up our integral. So we're going to have, this is equal to the double integral across this region D. And it's going to be the partial derivative with respect to x of the y term, which is xy squared, minus the partial with respect to y of the x term, which is, let me distribute that x. So it's going to be x squared plus xy dA. And that's going to give us the double integral over region D of, this would be y squared minus the partial with respect to y, the x term would go away. Partial xy with respect to y would just be x dA. Okay, and now we want to look at what the equations are for these lines. So we would have, okay, I'm looking at these again, and I notice I did make a mistake. The line segment 0, 3, that is back, that is not there. Zero, 3 is along the y-axis. So the dot is actually right here. that is 0, 3. So we're actually going to go from here to here. That didn't change, the bottom segment didn't change, but then we go up this diagonal, and then we go down to the origin. And it's still a counterclockwise orientation, so it's still positive. That is D. Okay, perfect. Okay, now we have to come up with the equations for these lines. So this bottom equation is the line y equals 0. This one diagonal line, if you were to use slope formula and calculate this, the y-intercept is 3 and it has a slope of negative x. So that would be the equation for that one. And those are going to be the limits of integration on our y term. Well, let me leave that. So we're going to get this is equal to, x is just going to go from 0 to 3, y is going to go from 0 to 3 minus x, bottom curve to top curve, and then we have y squared minus x, and we're doing y first and then x. So we're going to get 0 to 3. Antiderivative of y squared with respect to y is y cubed over 3. Minus the antiderivative of x with respect to y would be xy. And that goes from 0 to 3 minus x dx. And that is going to give us 0 to 3 of 3 minus x cubed all over 3 minus x, 3 minus x, and then we have dx. Now, it's not the nicest thing in the world. You have something to the third power. Probably the easiest thing here. Actually, you can do u substitution, so you'd want to use u substitution here. And if you do that, you will get, let's see, what do we get here? After you integrate and you put in after you expand this, you should get 0 to 3 of minus 1/3 x cubed plus 4x squared minus 12x plus 9 dx. Okay, and then when you take the antiderivative of this, you should get minus 1/3 x to the 4th over 4 plus 4 x3 over 3 minus 12 x squared over 2 plus 9x, and all of that is evaluated from 0 to 3. And if you plug in 3 here, I'm not going to show every step here, you should get 9 over 4. So our Green's theorem work, so the work done, and again we don't have units, so we can't tell exactly what the units are for this work, but a particle has moved in this triangular orientation, and we can calculate the work that has been done via the vector field. Problem 5. Okay, in problem 6, they give us, use one of the areas below to find the area under one arch of the cycloid x equals t minus sine t, y equals 1 minus cosine t. So we have a cycloid is kind of this shape that just, it's kind of like a bouncing ball, just keeps going like that. And we're only interested in this first one. So we just care about the first one arch, it says. So our area is D right there. Okay, so what we can do is we can say that x equals, let me write this a little larger for us, t minus sine t, y is 1 minus cosine t, and we have a is going to equal negative line integral of minus c y dx, which we're going to form into two curves. We're going to have c1y plus c2 y dx. And so basically this curve is going to go clockwise, so it's negative, and that's the negative c here, so this is a clockwise curve. And it's going to come back to the origin. We have to make it come back to the origin. So we have, this is c1 and this is c2. Okay, so we break this into two line curves, line integrals, and this is going to equal the integral from 0 to 2 pi of y, 1 minus cosine t, times the derivative of x, which would be 1 minus cosine t. So this is the derivative of x with respect to t. So it's y dx dt. And then we can make this with respect to t. That is the first curve. Then we're going to have plus 0 to 2 pi of the second curve, but the second curve's y value is 0. So it's just going to be 0 times dt, which the second curve is not going to contribute at all in this case. So we just have to look at this first curve, and we're going to FOIL that out. So we're going to get 0 to 2 pi 1 minus 2 cosine t's after we FOIL that, and then plus cosine squared t dt. And if you go through and take the antiderivative of this, you'll get t for 1. We'll get minus 2 sine t for the second term. For this term, you have to use a for this term, you have to do integration by parts, and you will get this. I think we actually saw this exact problem, cosine squared t integration by parts, in an earlier homework set. 1/2 t, after you take the antiderivative, plus 1/4 sine 2t. Actually, as I'm looking at that, that's either integration by parts or it might be a double angle formula. So I think you can get there either way. Okay, and then we're substituting in 0 to 2 pi. And if you do that, so again, maybe I can do some of this. So it's going to be 2 pi minus 2 sine of 2 pi, which is 0, plus 1/2 of 2 pi, plus 1/4 sine of 4 pi. That's all just the 2 pi one, minus, if you plug 0 in here, because every term has a t in it, and sine of 0 is 0, the lower limit when you plug it in is all 0. This is going to give us 2 pi. Sine of 2 pi is also 0. Sine of 4 pi is 0. So we get a pretty simple result. It's 2 pi plus 1/2 of 2 pi, which is 1 pi. The answer would be 3 pi. And that would be problem 6, cycloid, and we actually did the line integrals, not Green's theorem double integral. Okay, for problem 7, we have a rectangle. Okay, for problem 7, we have a rectangle that has the coordinates, let me use color, A, B, and the origin. So it starts at 0, 0. It goes to A0, and then it goes up to the dot A comma B. And it says A and B are both positive, so it's going to be in quadrant 1. Okay, so if we draw this triangle, it's going to go from 0, 0 to this point, then up to this point, then down to this point. So this looks exactly like the problem I had drawn incorrectly from the previous problem. And this is the region D. And basically they want us to find the centroid of this particular shape. And so the centroid is going to lie somewhere like right here, and we're going to call that point x bar comma y bar. And again, the centroid would be like the point of, so if we're thinking of like gravity or something, it would be where everything is balanced out. And this problem is a little more involved than I wanted it to be, so yours problem should not have any numbers different. So it turns out, and again, I don't want to go through this because it's a little longer than I want, the x value will be exactly 2/3 the overall distance, and the y value will be exactly 1/3 the overall height of that triangle. And so just record those answers and you should be good to go. If you are curious about it, I can show it to you, but it's quite a bit of work because you have to do these 3 curves. So you have to look at, you have to do C1, then you have to do this curve going up, which is C2, then you have to do this angled curve down, which is C3. You have to do 3 line integrals and add them all up, but you get the same answer. Okay, that'd be problem 7. Okay, problem 8 is more like, and I should mention, so if I just totally blew past 7 and didn't show you any steps, I would not expect a problem like that on the test. I'm not going to ask you something that I never showed you how to do. I just gave you the answer. But let's look at 8. This is one that I might ask because this one's more in line of what types of problems I would like to look at. So we have a sine curve going from 0 to 0. And they want us to calculate going from the first part of the sine curve. And so I believe we're going to go up like this, but then we got to get back to the origin. So we're going to go this way. So it's going to look like that. And because we are going clockwise, this is going to pick up a minus sign. So we're going to have a minus sign when we do our double integral. Okay, well, let's see what our double integral would be. We have the double integral of the partial derivative with respect to x of the first component of the vector field, second component of the vector field, 2x squared plus root y minus the partial derivative with respect to y of the first component of the vector field, root x plus 2y cubed. And that's going to be dA. This is going to give us, this will be 4x, square root of y will go away, minus, this will be 6y squared, dA. And we have y goes from 0 to sine x. And x goes from 0 to pi. So we can set this up, 0 to pi, 0 to sine x, and we forgot our minus sign. There should be a minus following this because of the clockwise nature of our curve. And we have 4x minus 6y squared with respect to y first, then x. So we get negative 0 to pi. Antiderivative of 4x would be 4xy. Antiderivative of 6y squared would be y cubed over 3. From 0 to sine x, dx now. This is going to equal negative 0 to pi. This is going to be 4x sine x when you replace y with sine x. And minus 6 divided by 3 is 2, and this will be sine cubed x. And then I don't need 0 the lower limit because both terms will go away. Okay, to do this integral, you want to use a u substitution. So this one you use integration by parts. And this one you're going to change into 1 minus cosine squared x times sine x. And that's dx. This one you're going to use a u substitution. Well, how did I get that? First off, well, we can write sine cubed as sine squared times sine. But sine squared x, using this formula here, 1 equals cosine squared x plus sine x squared, sine squared x. You can subtract cosine squared from both sides, and you can get this is equal to 1 minus cosine squared x times that sine that we had factored out. And the reason you want to do that is you can let u equal cosine. So if u equals cosine, then that's u squared, and then this would be du. So you can do that one with u sub, and this one you would have to do with integration by parts. So not the easiest thing in the world, but we can do it. I have shown you. And if you do this, when you plug everything in, you should get this thing will simplify to negative 4 pi plus 8 over 3, and I think I just switched the order here, 8 over 3 minus 4 pi. So that would be the setup. I did skip a few integration steps there because by the calculus 3 level we expect that you could do a u substitution or integration by parts, topics we taught in Calc 1 and 2, without me showing you every time. Problem 8. Okay, problem 9 says use Green's theorem to evaluate the line integral of f dot dr. Check the orientation of the curve first, and we have f of xy is this complicated looking thing. C is the circle x squared plus y squared equals 9 oriented clockwise. So this truly is a circle centered at the origin with radius 3. So this is D. This thing is oriented, what did it say? Clockwise, so it is going this way. So because of that, we are going to pick up a minus sign in front of our double integral, and this is a radius 3 circle. So let's also record that. So x squared plus y squared is r squared equal 9, therefore radius is 3. So we can jump right into our double integral. We would have minus double integral region D of partial with respect to x of the y term, which is e to the 3y minus xy squared, minus partial derivative with respect to y of the x term, which is e to the 3x plus x squared y. And we're going to do dA. So we're going to get minus partial with respect to x of this first term, e3y will completely go away, and this would be minus x would just become minus 1, so it's minus y squared. And this is minus partial of the second term with respect to y, e3x will completely go away, and x squared y, the y would become 1, and this would be just x squared, dA. But let's use polar coordinates since we're dealing with a circle. So we can change this. So first off, I can factor out a negative. So this is like negative d negative x squared plus y squared dA. And then those two negatives will cancel. So that will cancel with that. And we can write x squared y squared as r squared. And we can change dA to polar coordinates, which would be r dr d theta, if you remember back to that lesson on polar coordinates. So we would have, this whole thing would become just r squared times r dr d theta, and r is going to go from 0 to 3, the radius of the circle, and theta is going to go from 0 to 2 pi, the entire 360 degrees around the circle. So we get 0 to 2 pi. Now, this is a little trick that you'll sometimes see. Because d theta and r are completely separated, there's no overlap between those two variables. I can completely split, instead of having an integral inside of an integral, I can split them next to each other and multiply. So we're going to get 0 to 2 pi of d theta times 0 to 3 of r cubed dr. The first one is just going to be theta from 0 to 2 pi. The second one is going to be r4 over 4 from 0 to 3. So we're going to get 2 pi minus 0 when I plug in the limits times 3 to the 4th over 4 minus 0 to the 4th over 4. This whole thing will just be 2 pi times 3 to the 4th over 4. And if you do that, you'll get 81 over 2 times pi when you simplify that. Okay, so that would be the line integral of that curve, or the area of that region. Now, it doesn't quite represent the area of that region because that's not what the area would be if you just did the area of that. So it truly is the line integral of that curve. Okay, so that's problem 9. Okay, last problem is pretty similar. We've got another circle. This time it's shifted 5 to the right and 4 up. So the center is right here. And it has a radius of 2 now. So 4 is equal to radius squared. So therefore radius is 2. So we would have 1, 2, this one's down here, 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 and over here. So this is the circle. Another circle, and it says oriented counterclockwise. So this one is going this way. Counterclockwise. So our double integral will be positive. So we do that double integral, and we're going to have partial x with respect to the y component to arctangent of y over x minus the partial with respect to y of the first component, y minus natural log of x squared plus y squared dA. Now the derivative with respect to x of arctangent of x is 1 over 1 plus x squared. We're going to need that. And we're going to recall that the derivative with respect to x of the natural log of some function g of x is equal to g prime of x over g of x. So we need those two refreshers on those derivatives to get this. So we're going to have the antiderivative of, so the partial derivative of 2 arctan with respect to x is going to be 1 over 1 plus that whole thing, y over x squared, times the derivative of the inside part, which is y over x, which is the same as y to x to the minus 1. So the derivative of that would be minus x, minus y, x to the minus 2. So we're going to get, let's see here. Let's leave that as it is. Then it's going to be minus, partial with respect to y of this one's going to be 1 minus 1 over x squared plus y squared times the derivative of that function with respect to y, which would be 2y dA. So we get 2, negative 2 y over x squared over 1 plus, I think I want to distribute that square, y squared over x squared. And then this is going to be minus 1 plus double negative 2y over x squared plus y squared dA. Now where do we go from here? This is a bit messy. Make sure I didn't make any errors. Okay, this looks correct. Okay, so this one is interesting. I'm not going to go through all the algebra steps, but if you create a lowest common denominator for this, this first fraction and you combine like terms and everything, it will turn out to be this. It will be 2y over x squared plus y squared. And there's a minus in front, so it's actually minus 2y over x squared plus y squared. Then it's minus 1, then it's plus 2y over x squared plus y squared dA. And if you look very closely, again, I haven't shown this step, so from here to here, algebra, specifically find a lowest common denominator. And you'll notice, oh, the first term and the third term are exactly the same, but they're opposite in sign, so they will cancel each other. And we are left with minus 1, so it's minus 1 can come out, d of dA. But we know what dA is. It's just the area of this circle of radius 2. So it's just minus 1 times pi times radius squared, or minus 1 pi times 2 squared, or minus 4 pi. And that would conclude the last problem in chapter 16, section 4 on Green's theorem.